start the worksheet, let me remind you about the course evaluation. So the course evaluation is available on Blackboard right now. Please complete that. If you complete that, you will get 3 bonus points. So there's opportunity to earn bonus points. So it will be available until the end of this week. So please complete that as soon as possible. And once you complete that, you can email me that you completed that, and you will get 3 bonus points. Okay, so let's look at number, which one? I think we have done all but one. Is that the last one that we haven't done? Okay, so we haven't done the last problem about the pulley. So a pulley of mass 6 kilogram and radius 20 centimeters is mounted on a frictionless axis as shown in the figure. A massless cord is wrapped around the pulley while its other end supports a block of mass 3 kilogram. If the cord does not slip, find the linear acceleration of the block, the angular acceleration of the pulley, and tension in the cord. So we want to find angular acceleration, linear acceleration, and tension. So for that, let's draw free body diagram. Is this number 4 or 5? Because I have the older version of the worksheet. Yeah. Is it 3? Oh, we only got 2 problems done? So there's one more before that, right? That means. Okay. So let's first do number 4, and then we'll go back to number 3. Okay, I thought like we already did number 3, but if we haven't done that, we'll do that later. So for number 4, we have this wheel or pulley. Okay, and there's a mass hanging on this string. So when you let go of this mass, it will go down at some acceleration a, and there would be counterclockwise rotation in this pulley. So that means the rotation in this is due to some torque, and the torque would be provided by this tension, okay, tension of the rope. Okay. And this block has some weight. So if we draw free body diagram for this block, so there would be weight of the block, and there is tension T. This weight would be longer than tension because there is this net force or net acceleration down. So that's the free body diagram for the block, and this is the acceleration that we want to find. And we also want to find tension. So we can write Newton's second law for that block. So F along y direction is mass times acceleration along y direction, and we need to choose the coordinate. So let's choose the coordinate with the positive along the direction of motion. So this is positive, that's negative. So what's the force on y direction? We have weight down is positive, tension T up is negative, mass acceleration is pointing down, so it's positive. Okay. So we have this equation and we want to find T and A. Since there are two unknowns in this equation, that means we cannot use this equation. Okay, this equation won't give us what we are looking for. Let's just write this equation 1. So that means we need to look for a different equation. So what other equation we can use here? Since this disk is rotating, that means we can use this Newton's law for rotational motion. Okay, for rotational motion, we can write this as sum of torque is equal to mass is moment of inertia, acceleration is alpha. Okay, so use this for this pulley. So what's the torque on the pulley? Torque is what's the definition of torque or formula for torque? Fr sine theta. So what's the force that is providing the torque here? It's tension, right? And what's the distance between this point where you apply the force and the center? It's the radius of the pulley, and the angle between this distance and this force is 90 degrees, which is sine 90 degrees, which is 1. So we don't need to write that, it's just 1. I and alpha. Okay, and here this wheel is rotating in such a way that there is no slippage between the cord and the wheel. For no slipping or slippage, the condition is A is equal to alpha times R. Okay, that's the condition for no slipping. So that means we can write T R is equal to I, alpha is, so replace that alpha by A over R. So A over R. In this equation also we have two unknowns, T and A. So we have two equations with two unknowns. So all we need to do is eliminate one of the unknowns. Okay, so you either eliminate T or eliminate A. So whichever you want to do. Okay, so let's eliminate T. So write this in terms of T. T is equal to W minus MA. So you replace T by that expression. So then T, not T. So T is replaced by W minus MA times R is equal to I A over R. Okay. Now all you need to do here is write this equation in terms of A, because we are looking for A. So let's call this equation 3. Write equation 3 in terms of A. So let's do that. W is weight, M times G, mg. This one? This side? This is tension, yeah. That's the tension. All we are doing here is writing the Newton's second law for this block. And this block is moving down. That's why there is acceleration.
So the tension times the radius is the torque.
Yeah, so this is for the pulley. So, and that's for the hanging mass. Okay. So again, W is mg, and then we have ma times r. Now I is the moment of inertia. Since we are dealing with pulley, so we need to think about what's the moment of inertia of pulley. Pulley is a kind of a disc. Okay, so if you look at the moment of inertia for different objects, the moment of inertia for a disc, okay, is 1/2 mr squared. So any disc that rotates about its center is 1/2 mr squared. So we can replace this I by 1/2 mr squared, and then we have A over r. Okay. So again, all we need to do here is write this in terms of A. Okay, so we need to write or find an expression for A. So let's simplify everything. So you can take this r to this side. So there is m and m, so you can take m out of the parenthesis, m g minus a, and then multiply both sides by r, or you can take this r to the left. Okay? So we want to get rid of this r. To get rid of this r, either you take this directly down to up here, or just multiply both sides by r. If you do that, you'll get r squared. So 1/2 m r squared, and then a, so r over r would be 1. Yeah, again, just multiply both sides by r. That's what I did. So you get that. Now this m and this m can cancel, and then r square cancel. So what's left here? So g minus a is equal to a over 2. Okay. Now again, our purpose here is to get a. So g a over 2. So this a goes to right, becomes plus a. So that's 1/2 a, and a would be 3/2 a. Sorry, which one here?
Over on this side with the 1/2 mr squared.
Here?
Yeah. Does that need to be times by r also?
If it were plus, yeah, you need to do that plus. But if it is multiplication like that, it doesn't matter. So because of this multiplication sign, you can cancel this r and that r. But if you have a plus here, then you cannot do that. You will need to multiply to both the terms. Oops. Does that make sense? It's a simple math. You can do in other ways also. Now we have what's left here. G is equal to 3a over 2. So write in terms of a. So a would be 2 over 3 g. Okay, 2 over 3 g is 9.8 meters per second squared. So if you do the math, you get 6.5. Okay. Just a second. I think I messed up something here. I will need to make some correction here. This is very, very important. Can you guys point out what I made, what kind of mistake I made? So you learn lots of things when you make mistakes in physics. Okay? Because you will realize like what kind of mistakes you made, and then in future you won't make those kinds of mistakes. So mistakes are integral part of learning in physics. So tell me what mistake I made here. So we are dealing with two different objects here. One is this hanging object and this one pulley. Okay, so we cannot use same m for both because they are not same. So you need to consider one to be m and other to be either m2 or capital M. Okay, so you need to have different masses. So for hanging mass, I'm using small m, small m, small m. That's fine. But here, for pulley, I cannot use small m because this is for pulley. So that means I need to use a different mass here, capital M. Okay, so this is the moment of inertia of this pulley. So we need to use capital N here. So wherever I have I need to use capital M. So this I is that. That means here I need to use capital M. Okay, that's where I made the mistake. So let's see. I cannot cancel this M now. Okay. So keep that as it is. Here I need capital M. Okay. So I'll just redo the steps from this part, okay, so that you don't get confused. Okay. So let me erase that. I'll redo from here. So ID is same here, except just I messed up the two masses. Okay, so I multiplied both sides by R, so we have M common, G minus A, okay, times R squared. R and R is R squared, is equal to 1/2. Now here again it's capital M for pulley, mr squared. This R and this R cancel, so times A. Okay. Now I cannot cancel this M and this M because one is small m, other one is capital M. But I can cancel this R squared and R squared, same. Okay. So M, let's just not take M out because somehow I need to put A on same side. So mg minus ma, 1/2 ma. Okay. I distributed this m because I need to combine this term with this term, so I need to distribute this. So now,
Cancel each other out.
which one?
They wouldn't cancel each other out since there's
Which ones you mean?
M and A, since there's two on each side.
Again, the masses are different here. One is big M, other one is small m. So again, the thing we want to do here is to put the terms with A on one side and the terms without A on other side. So mg, keep that on the left side, and then take this ma to the right. Okay, 1/2 capital Ma plus small ma. Okay. Now you can take A common, so 1/2 big M plus small m. Okay. And now write this in terms of small a. That's what we are looking for. Okay. Oops. This is very sensitive. So we have mg, or divide both sides by this term to get rid of that. So 1/2 m plus m, okay, is equal to 1/2 m plus m. So I'm trying to get rid of that. That's why I'm dividing both sides by that. Times a. So cancel that. So now a is equal to mg over 1/2 big M plus small m. Okay. Now you can plug in the numbers. So small m is 3 kilogram. G is 9.8 meters per second squared. 1/2 big M 6 kilogram and small m is 3 kilogram. So let's see what you get. So when I did the calculation, I got 4.9 meters per second squared. So let's see, someone has okay, so the question says G is 10. You can use 10 here if you don't want to use 9.8, but that won't make much difference. So you use either 10 meters per second squared or 9.8. Both are fine. Okay, even if it says 10 meters per second squared, if you use 9.8, that's perfectly fine. I won't take a point for that. Okay, that's good. So we got A. Now let's look at the second part. So second part, it is asking to find tension. So to find tension, you can use either one. We have two equations. Let's see which one we want to use. So you can use either this one or equation 1 or equation 2. So let's use equation 1. So use 1 to find T. So T is equal to W minus MA, mg minus MA, or this is mg minus A. Mass, here we are talking about the hanging mass. So M here is the hanging mass, which is 3 kilogram. G is either 10 or 9.8, and A is, we just found that, 4.9. Okay, so when you do that calculation, you get 14.7 Newton. And it's also asking for the linear acceleration of the pulley. So we have this condition for rotation without slipping. Alpha is equal to, or for rotation without slipping, A is equal to alpha times R. So we want to find alpha. Alpha would be A over R. A is 4.9 and R is the radius of the pulley, which is 20 centimeters. So change that centimeters to meters. So 0.2 meters. And that will give you, so then alpha would be, I don't have answer for that. You can find that out. So divide 4.9 by 0.2 and see what you get. Okay, so that would be the alpha for the pulley. So that's number 4. Now let's look at number 3. 24.5. Okay. Okay, now let's look at number 3. So a uniform rod of length 1 meter and mass 0.2 kilogram is pivoted at one end. So that's the pivot. If it is held horizontal, okay, like that, and released, the pivot is frictionless. find the angular acceleration of the rod immediately following its release. So the rod will rotate like that about that axis. So we want to find what's the angular acceleration at which it rotates. It will rotate like that. Okay. So what is causing this rotation? Whenever you see a rotation, the rotation is due to torque. Okay, think about this conceptually. Due to torque, and the torque is produced by or provided by which force? Torque is always provided by some force. What's that force? What is pulling the rod down? Gravity or the weight of the rod, right? By the gravity or weight of the rod. Now, at what point the weight is concentrated? So the weight is always concentrated at the center. So that's the point where it is concentrated. That means the force is applied or the gravity is acting at the center. So that's the weight, and that weight is causing the rotation or providing the torque. So Newton's second law, tau is I alpha, and that's what we want to find. So let's use that. So torque is again force times distance times sine theta. Tau is Fr sine theta. So force here is W, weight. Distance between the point where you apply force and pivot, that's the R, which is 1/2 the length of the rod, and angle between R and weight is 90 degrees. Now I is the moment of inertia of the rod, okay, which is something you can find from the book. So when you rotate a rod about its end, then its moment of inertia is given by 1/3 ml squared. Okay. So there are two ways you can rotate a rod, or different ways you can rotate a rod. Like if you remember from the last week's lab, not last week but week before that, so we rotated a rod about this center. Okay, so we had the two masses and we had this axis, and we rotated the rod like that. You can also rotate a rod about this end. Okay, so you can rotate like that or that with this as axis. In this case, this is our axis. If this is the axis, the center is the axis, its I would be 1/12 ml squared, which is what we used in lab. But here, for this axis, it's 1/3 ml squared. Okay, so different axis produces different moment of inertia. So here, 1/3 ml squared is the moment of inertia times alpha. Okay, everything here is known except alpha, so we need to find alpha. Mg, okay, W is that, L over 2, sine 90 is 1, 1/3 ml squared alpha. M and M cancel. This L and one of the L's cancel. So this 3 you can take to the left, so 3/2 G over L is alpha. Okay, so alpha is 3/2 G over L. 3/2 G is 9.8 meters per second squared. Length of the rod 1 meter. So if you do that calculation, you get 14.7 radian per second squared. Okay, double check that calculation. Okay, so that's worksheet 19. Let's look at worksheet 20. You can find worksheet 20 on Blackboard if you are on Zoom. So previously we talked about conservation of momentum. Momentum before is equal to momentum after. Now we can use the same concept for rotation also. Okay? When something rotates, just like when something is moving at some velocity, its momentum is given by mass times velocity. When something is rotating with some velocity omega, okay, in case of rotation, this v is replaced by omega and mass is replaced by I. So in this case also we will have angular momentum. So this is called linear momentum. In this case we will have angular momentum. Angular momentum is denoted by L. L would be, can you guys guess what that would be? Yes, exactly. So M is I and V is omega or W. It's omega. So that's the moment of inertia. Okay. And moment of inertia is always conserved in any kind of process. Just like when there is collision between two masses, moment of inertia before is equal to moment of inertia after. Here also we can have angular momentum before is equal to angular momentum after. Okay? So the conservation of angular momentum states that angular momentum before is equal to angular momentum after. You can write angular momentum before as Li and angular momentum after as Lf. Li is that I times omega I, and final angular momentum is Lf is If times omega f. Okay, so that's what we are going to apply for worksheet 20. Number 1, a circular disc of mass 5.5 and radius 28 centimeters. It is dropped on the top of another circular disc that has mass of 14 kilogram and 20 centimeter radius, and that is already spinning at 650 radian per second. The discs eventually spin at the same rate. What's their final angular speed? combined moment of inertia of that disk. Now we have another disk on top of that. We drop that. Okay. And then after dropping, we'll have combined disks, one the bottom one and one on the top. And for the combined one, the moment of inertia would be moment of inertia of disk plus moment of disk 1 plus moment of inertia of disk 2, and its final velocity will be WF. This is what we need to find. So initially we have one disk that is rotating at that speed, and then we drop another disk over that, and then it will rotate at different velocity. So this is before dropping, that's after dropping, and we know moment of inertia before is equal to moment of inertia after. So before, it's I on that disk. This is at rest, so we don't need to worry about the moment of inertia of that, because omega for that is 0. So here it's disk 1. Okay. Moment of inertia is that of disk 1 times speed or velocity I. And then after, we have moment of inertia of disk 1 plus moment of inertia of disk 2. It's like we are combining same kind of problem. So we have two objects colliding each other, and after collision they become one. So we take M1 plus M2 as a combined mass. Here we take I1 plus I2 as combined moment of inertia times final angular velocity. Okay. So we are just using that here. Total moment of inertia before collision, total moment of inertia after collision. So rest is just using the formula. So I disk is 1/2 first disk times radius of first disk squared. I think they are identical. No, they are not identical. Although they have same radius. So call that M1R1 squared omega I 1/2. This is the first disk R1 squared. Because they have the same radius, so I don't need to use R1 here. I can just use R. Okay, so let's just use R because they have same radius. Plus 1/2 moment of inertia of the second disk, its mass times its radius squared. Again, radius is R for both the disks. Okay, so that's radius is R, that radius is R. Both are 28 centimeters. And omega F. So we need to solve this equation to find WF. If you want, you can plug in your numbers at this point, but you can further simplify. But can you guys tell me like what you can do to simplify this? There is something you can cancel. So let me write one more step and you will see how we can further simplify this. So we have 1/2 on both the terms, so you can pull it outside the parentheses. What else is common in these two terms? Yeah, so we can pull that out. Anything that is common, you can pull that out. So M1 plus M2 is left inside. Okay. So 1/2 on right side, 1/2 on left side. R squared on one side, R squared on the other side, so we can cancel common terms. So M1 omega I M1 is 5.5 kilogram. M1 5.5 kilogram. M2 14 kilogram. And then double I 650 radian per second. Okay, so you do calculation and you get double that. So my answer is 183.3. I may be wrong, so please do the double check that calculation. Okay, so please check the calculation. I may be wrong. Okay. So that's how you do that. Now let's look at the second problem. Second is similar one. I think you guys should be able to do that. Look at a physics professor stands at the center of frictionless turntable. So the person is standing on a rotating surface with the arms outstretched and a 5 kilogram dumbbell in each hand. He is set rotating about the vertical axis, making one revolution in 2 seconds. Find its angular velocity if he holds his dumbbell close to his chest. His moment of inertia is 3 kilogram meters squared with arms outstretched and 2.2 kilogram meters squared with his arms are pulled in close. It should be, there is a sentence error here. When his arms are pulled, so that width should be when his arms are pulled in close to his chest. The dumbbells are 1 meter from the axis initially and 2 meters at the end, 0.2 meters at the end. Also compare the final kinetic energy with the initial values. So the idea here is again total angular momentum before is equal to total momentum after. Okay, before in case, sorry, here is after. Here before means before stretching the hands, after means after stretching the hands. So I, total angular momentum is I times omega. I initial, omega initial. Momentum is I times omega. I final, omega final. And we want to find omega final here. This is what we want to find. So what's the I initial? So if you remember from the lab last time, so when we found the moment of inertia of this rod with the mass, how did you find the total moment of inertia of that system? So total moment of inertia is moment of inertia of the rod plus moment of inertia of these individual masses. So the total moment of inertia is moment of inertia of each individual components. Here, in case of the rotation, there is a person and there are 2 dumbbells. So that means moment of inertia would be I of the person or professor plus I of dumbbells. And this is arm stretched. Okay? also we have two things. One is I of professor plus I of dumbbell, and this is for arms folded. Omega F. So for the stretched arms, and for the stretched arms, I professor is, what's that? 3, yeah. So this is 3 kilogram meter squared, and I dumbbell. So the moment of inertia of each dumbbell is m times r squared. Okay? M times r squared. That's the moment of inertia for dumbbell. So that means 2 times, because there are 2 dumbbells. So 2 times mass of the dumbbell, 5 kilogram. Distance of the dumbbell from the center of the body, 1 meter. When the arms are stretched, it's 1 meter far from the center. Okay. And that's the moment of inertia total. And this omega I is, what's omega I? If you read the question, the second sentence, he is set rotating about the vertical axis, making 1 revolution per second. So omega here is 1 revolution per second. In 1 revolution, what's the angle made by the person? When you make 1 revolution, what's the angle you make? 2 pi, right? 2 pi radian. So you make 2 pi radian in 1 revolution. So that's the initial angular speed of the person. So omega I is 2 pi radian per second. Okay. Now I, after folding the arms, if you read the question, it says 2.2 kilogram meter squared. Oh, there's, okay, so there is someone pointed out that point. I think I did something wrong here. Yeah, so it's over 2 seconds, not 1 second. So this is 1 revolution per second. It says 1 revolution 2 seconds. So here on the bottom it's 2 seconds. So that should be pi radian per second. Okay. So that's just pi, because it makes 1 revolution every 2 seconds. So 2 pi over 2 seconds. Thank you for pointing that out. So then that's the moment of inertia of the professor, and then moment of inertia of dumbbells. 2 times 5 times distance when the arms are folded would be 0.2 meters squared. Okay. That's the moment of inertia after folding the arms, and then double F is unknown. So here in this question, in this equation, everything is known except double F. Okay, so find that.